Section 9.1 deals with what are known as sequences. A sequence is a function whose inputs are natural numbers 1, 2, 3, 4, 5, 6, and so on, and whose outputs are real numbers. Typically, we use the notation S sub n to denote a sequence. So, for example, here I have S sub n is 3, 6, 12, 24, 48, 96. The ordering matters. So we would say S1 is 3, S2 is 6, S3 is 12, and so on and so forth. So like any function, we can represent it three ways. We can use the formula. S sub n is 3 times 2 to the n minus 1. Notice that if n is 1, this would all just be 2 to the 0th, which is 1, so we'd have 3 times 1, which is 3. If n is 2, we'd have 2 to the 1st, which is 2 times 3, which is 6, and so on and so forth. So here's a formula representation of the sequence S sub n. But we can also represent a sequence using a table of values. For each value of n, I can use the corresponding value of S sub n that I got from that formula. And finally, we can represent a sequence using a graph. A nice graph like this one, where the input values are nothing more than natural numbers and the output values are just plotted as dots. We don't connect the dots at all. So let's take a look at some examples. Here's a sequence of numbers: 1/2, 1/4, 1/8, 1/16, 1/32. It's pretty easy to see a recurring pattern here. The numerator is always 1 and the denominator is going up by a power of 2 each time. So the formula for this sequence would be S sub n is 1 over 2 to the n. We can check this. If n is 1, 1 over 2 to the first is a half. If n is 2, 1 over 2 squared is a fourth, and so on. So this is a formula representation for this function. Here's another one. 3, 7, 11, 15, 19, 23, and so on. Notice how we start at 3 and we always go up in increments of 4. So it's 3, 3 plus 4, 3 plus twice 4, 3 plus thrice 4, 3 plus 4 fours, and so on and so forth. So this is what's known as an arithmetic sequence because we're always going up by a fixed amount, 4 in this case. S sub n is 3 plus 4 times n minus 1. Well, let's check this. If n is 1, this would be just 3. If n is 2, we'd have 3 plus 4, which is 7, and so on and so forth. Another example. One minus a half, 1/4, minus an eighth, and so on and so forth. Now, one thing we notice here is that the signs switch back and forth between plus or minus 1. And typically that can be accounted for by taking minus 1 to the n minus 1 power. Because if we take minus 1 and raise it to odd and even powers, it's just going to flip back and forth between plus and minus 1. The powers of n, the powers of the denominator, are going up by 2 each time. We're always doubling, except instead of starting at 2 to the first, we're starting at 2 to the 0th. In other words, we're going to use a 2 to the n minus 1 here. Let's check that this works. If n is 1, we'd have minus 1 to the 0, which is 1, over 2 to the 1 minus 1, which would be 2 to the 0th, which is 1. If n is 2, we'd have minus 1/2 to the first power, minus 1 to the first power, which is minus 1, over 2 to the first power, which is 2. If n is 3, we'd have minus 1 squared over 2 squared, which is 4, and so on and so forth. Okay, let me say that again. If n is 3, we'd have minus 1 squared, which is 1, over 2 squared, which is 4. Here's another example. 1/2, 2/3, 3/4, 4/5, 5/6, and so on. It's pretty clear that the numerator is always just the n value, be it 1, 2, 3, 4, 5, or 6, and the denominator is always just one more than the numerator value. So we could phrase this by saying that S sub n is n divided by n plus 1, and you can check that this works. Sometimes sequences are defined, well, here's one more. 1/2, 2/4, 3/8, 4/16. The numerator is always just going up by 1, and the denominator is always just a power of 2, starting at 2 to the first. So we could use S sub n equals n over 2 to the n. If n is 1, we'd get 1 over 2. If n is 2, we'd get 2 over 4. If n is 3, we'd get 3 over 8, and so on and so forth. In all of these examples, the sequences had explicit definitions, but that's not always going to be the case. Okay, but we can still sometimes notice a pattern. One very famous sequence for which this occurs is what's known as the Fibonacci sequence. You've probably seen it before. It starts 1, 1, 2, 3, 5, 8, 13, 21. Each term in the sequence is the sum of the two preceding it. Because each new term depends upon the preceding terms, we say that this is a recursively defined sequence. So a formula for this would be that S1 is 1, S2 is 1, and S sub n equals S sub n minus 1 plus S sub n minus 2, if n is 3, 4, and 5, and so on. So for example, if n is 3, S3 would be S2 plus S1, which is 2. If n is 4, S4 would be S3 plus S2, which is 2 plus 1, which is 3, and so on and so forth. Now, in Calculus 1, we look at the idea of a limit. If we want to look at the graph of a function, we might ask, what happens to the input variable, the output, as the input variable becomes larger and larger and larger? And we can ask this question two ways. We can ask, does the graph of f of x have a horizontal asymptote as x goes to infinity? Does the limit as x goes to infinity of f of x exist? Now we can ask the same question in the context of sequences. What happens to the value of S sub n as n gets larger and larger? So let's take a look at an example, n over n plus 1. I've made a table of values here. 1/2, 2 2/3, 3 3/4, all the way up. I stopped at 10, 10 11ths. And I also made a graph of the function. I graph the points as dots, and we can see that the height of the dots is getting closer and closer to 1, which is what the table also showed. How close to 1? Well, as close to 1 as we would like. So we write this in terms of a limit. We say the limit as n goes to infinity of S sub n is equal to one. We could have guessed this from the outset, because if n is large, n over n plus 1 is going to be pretty close to n over n, which is 1. In other words, the 1 in the denominator is fairly insignificant. So again, we can make the values of S sub n as close as we like to 1 by choosing n large enough. And this should remind us of the definition of limit from Calc 1. It's very similar. We say that the sequence S sub n converges to L if we can make the values of S sub n as close as we like to L by choosing n large enough. And we write this as the limit as n goes to infinity of S sub n equals L. If this limit does not exist, we say that the sequence diverges. Okay, this is the formal definition, not as n gets large, S sub n gets close to L, but S sub n converges to L if we can make the values of S sub n as close as we like to L by choosing n large enough. Okay, that's the formal definition. Let's take a look at some examples. We already looked at the sequence S sub n is n over n plus 1, and we saw that That's approximately 1 if n is large, so we wrote that by saying the limit as n goes to infinity of s sub n is equal to 1. We also saw that from looking at the graph. This is a 1 and that's a 2 and so on and so forth. Let's take a look at the sequence 1 over n. The table of values is 1, 1/2, 2, 1, 1, 2, 1/2, 3, 1/3, 4, 1/4, 5, 1/5, and so on. It's pretty clear also, if we plotted the points of the sequence as dots, that they are getting closer and closer to 0 as n gets large. So we would write this by saying the limit as n goes to infinity of s sub n is equal to 0. A slight variant. S sub n is minus 1 to the n over n. So the minus 1 to the n is going to flip the sign back and forth between positive and negative. For example, if n is 1, we'd have minus 1 to the first over 1, which is minus 1. If n is 2, we'd have minus 1 squared, which is 1 over 2. If n is 3, we'd have minus a third plus a quarter minus a fifth, and so on. In this case, the graph looks a little bit different. Instead of the dots just getting closer and closer to the origin, they flip-flop back and forth, but they still get closer and closer to the origin, so the limit as n goes to infinity in this case is equal to 0. Another example. S sub n is n squared plus n plus 1 over n to the third. I made a table of values here, 3.88, 0.48, 0.33, 0.25. They corresponded to values of n equals 1, 2, 3, 4, and 5, and so on. And I also plotted the sequence points as dots. Now you'll notice again that the output values of the sequence appear to be getting closer and closer to 0 as n gets large. And this makes sense because if n is large, the dominant power in the numerator is n squared. The dominant power in the denominator is n to the third, and 1 over n goes to 0 as n goes to infinity. So the limit of our sequence, s sub n, is 0 as n goes to infinity. Now how can a limit fail to exist? Well, here's an interesting example, the sequence minus 1 to the n. This does nothing more than flip-flop back and forth between minus 1, 1, minus 1, 1, and so on and so forth. I've plotted it. You can see the dots just flip-flopping back and forth. Because there is no value that we can make s sub n as close as we want to as n gets large, the limit does not exist. Sure, if n is odd, s sub n is very, very close to negative 1. If n is even, s sub n is 1. So it appears that there's two sorts of limits happening here, but the limit overall does not exist. Perhaps one of the most important types of sequences is what's known as a geometric sequence. A geometric sequence takes the form s sub n equals a times r to the n, where n is 0, 1, 2, 3, so on and so forth. There are different conventions. Some people start at 1, some people start at 0. Computer scientists tend to start at 0, so that's what we'll do. So a geometric sequence might be something like 1/2, 1/4, 1/8, 1/16, 1/32, and so on and so forth. Notice how S0 is just a, S1 is a times r, and so on and so forth. The a value is always the first value in your sequence, and the r value is always what you multiply one sequence value by to get the next one. Notice how I multiply a half by a half to get a quarter. I multiply a quarter by a half to get 1/8. I multiply 1/8 by 1/2 to get 1/16. So a is 1/2 and r is 1/2 in this case. So the formula for the sequence would be s sub n equals 1/2 times 1/2 to the n. And it's pretty clear that if we look at this sequence, the limit as s sub n of s sub n as n goes to infinity is equal to 0. Here's another example. 3, 6, 12, 24, 48. The first term is 3. The r value is 2. So for example, S0 would be 3. S1 would be twice that, which is 6. S2 would be twice that, which is 12, and so on and so forth. So in this case, S sub n is 3 times 2 to the n. It's clear that the values are getting larger and larger as n gets larger and larger, so we say the limit as n goes to infinity of S sub n, it does not exist. You could say it's infinite, and that would be okay here as well. Okay, here's another example. 5 minus a half, 5 quarters, minus 5/8, so on and so forth. Now how do we recognize whether it's geometric? We ask ourselves, are we always multiplying by the same number to get from one element to the next element? We multiply 5 by minus a half to get minus 5 halves. We multiply minus 5 halves by minus 1 half to get 5 fourths. We multiply 5 fourths by minus 1 half to get minus 5/8. So the r value, the quantity we're always multiplying by, is minus a half. A is 5. So for example, S0 is equal to 5. S1, if I use this formula, would be 5 times minus 1 half, or minus 5 halves, and so on and so forth. In this case, it's pretty easy to see that the limit as n goes to infinity of S sub n is equal to 0. In fact, for a geometric sequence in general, S sub n is going to go to 0 provided the common ratio value is between 1 and minus 1, like it was here and up here, but not here. Otherwise, the limit won't exist. So again, for the geometric sequence, the limit as n goes to infinity of ar to the n is 0 provided r is between 1 and negative 1. Now, tricks for other types of sequences. Rates of growth are very, very important. So let's recall some facts about rates of growth. A power function will always grow greater than another power function if its power is larger. So for example, n to the third grows faster than n squared. N to the fifth grows faster than n to the fourth, because 5 is greater than 4. But exponential functions grow faster than any power function. Oh, I'm sorry, exponential functions, yes, exponential function grows faster than any power function. That's what we have here. So for example, 2 to the n will grow faster than n to the third. 3 to the n will grow faster than n to the 18th. An exponential function always grows faster than a power function. An exponential function will grow faster than another exponential if its base is larger. So for example, 3 to the n grows faster than 2 to the n, because 3 is greater than 2. So, power functions, exponentials. The log function grows more slowly than any power function. The natural log grows more slowly than the square root of n, the cube root of n. And finally, the factorial grows faster than any exponential function. The factorial, n factorial, is n times n minus 1 times n minus 2 all the way down to 1. So, for example, 3 factorial would be 3 times 2 times 1, which is 6. Four factorial would be 4 times 3 times 2 times 1, which is 24. So let's take a look at some examples. S sub n is 3n squared plus n over n squared plus 1. We know that n squared grows faster than n as n gets large, so the top looks more and more like 3n squared. The bottom looks more like n squared, which is 3. So the limit in this case of S sub n is equal to, 3. N squared plus n over 2 to the n plus square root of n. Now in the top of the two powers, n squared dominates. In the bottom, we have an exponential function and we have a power function, the square root, but the exponential function grows faster. Now, what about the limit? The top is getting larger and larger. The bottom is getting larger and larger, but a power function does not grow faster than an exponential function. This exponential function gets larger faster, so the limit is equal to 0. And incidentally, if you wanted to use L'Hopital's rule here, that would be permissible as well. S sub n is the fifth root of n over 1 plus the natural log of n. Now if n is large, we have the fifth root of n in the top, and the 1 in the bottom becomes insignificant, so we have the natural log of n. So the natural log of n is getting large, as is the fifth root. But who's getting larger faster? Well, the fifth root is, because the natural log grows more slowly than any power function. So in this case, the limit of S sub n does not exist. You can also check by plotting the sequence. You will see the values have no horizontal asymptote as n gets larger and larger. Here's what I would like for you to do in preparation for class. I'd like for you to be able to state the formal definition of what it means to say that the sequence S sub n converges to L. For each of the following sequences below, I'd like for you to find a formula for S sub n if it's not given. That would apply to A. Calculate the first 6 terms and determine whether or not the sequence converges or diverges, making sure to explain your reasoning. And you can use ideas about rates of growth and behavior, but some sort of explanation. Okay? See you later.